Hello, everyone. Hi. Okay, so we are already the last week of lectures. Wow, time flies. So we are going to finish the generative model, the first part today, and we're going to start the second part. And in the Wednesday, we're going to finish everything. So we are done with all the contents I prepared for the semester by this Wednesday. And let me talk more about the plan after that. So first of all, homework 4 is due on this Wednesday. And as I said, this time, no deadline extension. So please submit your homework as you're ready. And also, I mentioned that all lecture recordings will be publicly available. And so far, everything is already uploaded. And you can actually look at any lectures so far in this course, and also from the last semester, which was taught in Korean. So if you have difficulties to understand the contents because of this English, you can also take the Korean lectures to study the prepare for the final exam. And thanks for everyone who subscribed me. As this is my only YouTube channel, so I wanted to say that well, thank for your subscription and thumbs ups and everything. And final exam, as announced before, it will be on next Monday in the classroom. So it's same as last midterm. So you are going to come to the data science building in building 942. And it's the same. So I think you're already familiar with the logistics. In the final exam, the coverage will be lecture 11 to 20, which is after the midterm range. So, but still, some questions might implicitly require some understanding of the materials covered before the midterm. I'm not going to directly ask those, but there will be still possibly implicitly required. And I uploaded the previous exam on ETL, so you can use that to prepare your final exam. And the questions will be in a similar style, but the questions will be different as last time. And after the final exam, we are not going to have the class in Wednesday. So you can use this time for projects, because the project deadline will be in the upcoming Monday, which is the 13th. And I have written the project presentation logistics here in more details. So in this semester, this project presentation will be online. So you just connect to this lecture as usual on 13th and 15th on Monday and Wednesday. And each team will have 5 minutes to present and 2 minutes for Q&A and grading. So I'll talk more about the grading below. And all the slides, presentation slides, needs to be submitted by the deadline of the final project, which is the Monday, 10 a.m., 1 hour before our actual presentation day. And you cannot modify the slides because some teams will present on Monday and the others will do on Wednesday. So to be fair, I'm not going to give you the chance to update, even though you presented on Wednesday. And about half teams will be randomly selected to present on Monday, and the rest will present on Wednesday. And I'm not going to give you the list until the first team starts. So you will know your presentation order and the date on that day, on 11 a.m. when we start the first presentation. But if you have any restriction, for example, if you have to take some flight on Wednesday, so you have to miss the lecture, you can schedule with me in advance, then I will try to accommodate. And regarding the grading, the final project is 150 points in total. 50 points will be based on your final paper. And the other 100 points will be based on your presentation. And for that, 50 points graded by me and 2 TAs. And the other 50 points will be graded by other students in the class. So I will call that peer review. So everyone actually needs to come and join this presentation day and you have to submit the grading form for all other teams. Otherwise, actually, this is required. Unusually, we require the attendance for this part because it is important to listen to others' presentations as well. So I'm requiring the attendance. And if you don't attend and if you don't submit the grading forms, then you're not going to receive the 50 peer review points for yours. So that's the rule. And the presentation will be recorded and will be uploaded to the course website. So practice a lot and dress up if you want. Okay, so any question about the presentations or final exams and any other schedules or logistics?
I have one question.
Okay, Chayan.
Do we have to present it in English?
Yes.
Okay.
Because, yeah, there are non-Korean students in the class, so they should be able to understand your presentation.
Okay, thank you.
Okay, thanks. Any other question? So anyone in the team can present, not necessarily the leader. So you can decide who actually presents. But I encourage only one member in the team actually present because this is online meeting and it's harder to switch the speakers and the presentation and so on, unless you're actually at the same, physically at the same location. Okay, so that is the announcements. And if you don't have any more questions, we are going to start today's discussion. So in the last lecture, we learned about autoencoders and variational autoencoders. So because we had to stop in the middle, I prepared this one slide, which is summarizing what is the variational autoencoders and what we discussed in the last lecture. So variational autoencoders actually tries to add some additional conditions to our first try, which was just modeling some PZ arbitrarily and add some generators on top of that to to generate the image. But that actually failed because we realized that that is just equivalent to minimizing the square distance between the images if we apply the Gaussian distribution assumption to this distribution. So in variational autoencoders, we explicitly force the PZ to reflect observed examples X, which is PZ given X, instead of just arbitrarily modeling PZ as a normal distribution. And also, because we don't know this PZ given X, we make another distribution called Q, which is parameterized by phi, and we model this to be as similar as possible to P. So we derived all the mathematical formula in the last lecture, which was this. So the final result was like this. The first part, the red one, is the reconstruction error. So actually, this is not loss function, but it's more like a likelihood. So we'd like to maximize the probability of X given Z, where the X is the real samples. So we're going to see how actually this is computed in the next slides. So this part is the reconstruction, which was equivalent to our first try, where we didn't have any assumption about the PZ. But in this variational autoencoder frameworks, we had the next two terms. So at the same time, we increase the probability of this PX given Z. We also had to minimize the KL divergence, or distance between two probability distribution, which is the Q and P. So QZ given X should be similar to PZ. So we enforce that the the Q is the encoder actually. We can call this as an encoder. We're going to see that in the next slides. Embeds the data point X to a prior distribution PZ, which we are assuming as a Gaussian. And the third term, we don't have any control because we don't know what is PZ given X. So this part is just considered as some additional term that we kind of approximate because we cannot model this, and we just know that this is positive, and we just accept it as an approximation. So that was what we have covered in the last lecture. So today I don't ask any question to you. So this is the overall structure of the variational twincoders. So here we see that this is our loss function. So this is coming from here. So because we don't have any control on the last part, we just ignore it. And the first two terms are negated here. So minus is given here, and this is plus, because this is the likelihood function. So we would like to maximize this. So loss function, we want to minimize something. So we just negate them to make it as a loss function. And here, the first term is the reconstruction loss, and the next term is the additional regularization term, which forces our encoder Q matches to some Gaussian distribution, which is PZ. So let's see. VAE, the variational autoencoder, is a generative model. This was the goal. Recall that this was the real goal of what we are doing. Unlike the autoencoders, where we just give the real examples and then we embed, so we get the vectors. So that was mostly used for representation learning. So at that time, I mentioned that we add this generator at the end of the Z to train this encoder part. Now it's the opposite. We temporarily attach the encoder Q to train the generator. And once it's trained, then we can use any Z to generate the realistic images. So this encoder part no longer needed because we don't have any more training data X. So this latent space Z is modeled such that actual examples Xi here mapped to the encoder Q are semantically well distinguished. So there are arbitrary realistic images in the data set, and whatever they are, this encoder needs to discover its distribution and maps those images into some space, embedding space, such that they still can be distinguished from each other. And based on that compact representation, we can use this generator to recover those images into more like realistic actual images. So that's what this part is doing. And at the same time, the embedding C is a Gaussian distribution. That is another assumption that we apply using this minimization of K divergence here. So as I mentioned, we are trying to model this Z as a Gaussian distribution. So now the encoder outputs the basic components of the Gaussian distribution, which is the mu and sigma. And using those mu and sigma, we sample from that Gaussian distribution to have this Z. And using this Z, we generate the actual images. So input image is represented in this way. Recall that what is an image? It's a two-dimensional matrix filled with pixels, and each pixels have some RGB scores, right? So they represented it as a binary map. So size m by n that's the image size, and the 3 is the channels RGB times 256, which is all the possible integer values for each pixel, right? So only one of these 256 per each pixel and per each channel will be 1, and all others will be 0. First, for example, in the red component of this particular pixel is like 5, then only 5 will be 1, and all other from 0 to 255 will be 0 for that particular pixel on that red channel. In that way, we encode the image into this 4-dimensional tensor. Okay? So image is represented as a binary vector of its size times possible pixel values, which is 256 times 3 RGB channels. So in this setting, everything is binary representation, one-hot vector. So we apply just negative log likelihood over all values. So given this is our loss function. It's copied from the previous slides. This part is the reconstruction loss, as I mentioned. So here, given this G, the generator, the probability distribution of this particular image, I, is represented like this. Because we have this form, we have 4 summations here, which is originally multiplication of these, assuming all of these colors are independent to each other. But because of this log, it was changed to summation, just like the maximum likelihood estimator. So each of these elements is represented as a loss, cross-entropy loss function like this. So if this real value for some particular location, some particular color, and if these this component was 1, the correct color, then this becomes 1. And then this term survives, and our model needs to output larger values for this particular one. And all other values in that pixel will be 0, other than this one. So then this term will survive, because this is 0. Then we also need to output lower value for those components by this model, so that we increase this term as much as possible. So because we have negation here, that becomes a loss function, and we want to minimize this entire term, which is equivalent to have larger output for actual pixel values in our data set, and smaller outputs for other values, which is incorrect values, as much as possible. In this way, we want to just we are training this model to output the images it has seen from the training data set. And later, it will once it tries to generate as many images as possible, which is from the training data set, then we expect that it will learn some patterns inside that data set. And if we change these z values using these mu and sigma values slightly, then we hope that this model actually generates other realistic images, which is not even different from the images that has seen in the training data. And the second part, the KL divergence part, it wants to minimize the KL divergence between the encoder and the PZ here. And I just omit all the mathematical derivation, but actually you can do this by applying the Gaussian distributions definition here. So the result looks like this. Once you minimize this KL divergence, apply this definition of KL divergence, and apply this PZ, and Q follows the normal distribution like this, then you're going to have this. What does it look like? In regression or classification in lecture 6, or I don't remember when it was 6 or 7 at the early part of our course, we have seen the regularization of the model. And there we learned about L2 regularization. Do you remember that? L2 regularization, what was that? We wanted to minimize the squared sum of the components in our model as much as possible to reduce the overfitting. That was the goal for the regularization, right? This resembles that, actually. This mu ij square plus sigma ij square. So minimizing the KL divergence, or the distance between these two distributions, is actually equivalent to minimizing the actual absolute value of those mu's and sigmas as much as possible. So we didn't intend, but actually, mathematically, we can prove this. So overall, this model is basically try to assign the high probability of the actual pixel values in the training data set. And at the same time, it wants to use small mu's and sigmas if possible. Right? So someone might ask this kind of question. We are using Z from normal distribution with very simple structure, just squared diagonal distribution, and only the zero-centered normal distribution, which is really simple. But the distribution of images in the data set can be really complex, right? We can collect like billion images from like a variety of topics. can we still use this simple representation to memorize or remember and distinguish all of those different topics in this small embedding space? It sounds unreasonable, right? So interestingly, the answer is actually that's enough. And how that was possible? Because we are using the deep neural network for this generator model. Actually, those complex stuff doesn't have to be in this embedding space entirely. It just provides the most important keys to distinguish them at the high level. And then distinguishing those in the fine-grained details can be still learned in generator. So we just modeled this probability distribution Z, which is Gaussian distribution. Only the most important details that this generator can still distinguish and the fine details of those images. And that's it. So this answer is really simple. We just use the deep neural network for the generator, then everything is fine. But yeah, here's the actual reason. So the lower layers of this generator still learns the complex manifold of the image space. And this probability distribution in Z itself just learns what it needs to use this generator. So just empirical results. I mean, they didn't intend this probably, but they realized that this is enough, and now they can explain or interpret how this is possible. So here are some examples. So they use the MNIST dataset, the handwritten digit dataset, to generate those numbers. And this is it. So they mapped the embedding space into two-dimensional space. And for each of those grid points, they generated actual images. And this looks like this. So we see that in each of these areas, here are most 6, here are 2s and 9s, 8s, something like that. And if we look at the borders between the two numbers, actually we see that, for example, 9s and 4s are some combination of those two, some intermediate number, which we might interpret as a 9 or 4, or people can just misunderstood. And here it looks like 4 and 7 are mixed, and it might look like 9. I don't know. So this is the manifold they have learned using the MNIST data set. And another experiment was done on facial expression data set. So this is the outcome. And we can interpret it like this way. Going to the top, it's less smiling. And to the bottom, it's more smiling. And the other direction is gazing to the right and gazing to the left. So probably this data set found out those two are the most distinguishable features in this data set. So here's the summary of the variational twincoders. So it's a principled approach to generate generative models. So in autoencoders, we were not able to actually generate the realistic images, but using the probabilistic modeling, it now enables us to generate actual images. And they used the variational lower bound, which is the third term in our derivation. So to optimize the intractable density, they derived all the things we have done in the last lecture, and that became the variational lower bound. So there are more details about these mathematical derivations, and actually there are two versions. I showed only one of them, but if you search on the internet, you're going to see the other one, which is highly related but slightly different. So you can actually use that also to derive this variational twincoders formula. The philosophy is the same, but mathematically it might look slightly different. And the pros and cons. So this is providing the interpretable latent space, just like this. We can interpret the latent space, what each axis means in the Z space. And we can use any arbitrary Z values to output, generate the images. And useful feature representation for other tasks. So we just embed the faces like this, and then we can use those Z as a feature representation of those vectors, those images, and we can learn, for example, face clustering or face classifications or anything. And the cons, this is actually interesting part. Working with a lower bound of likelihood. So the formula was approximation. It's not exact because we had 3 terms, but we just ignored the third one and only optimized the first 2. So this is not exact, and it doesn't provide any bound that the third term is actually negligible. So it's just approximation. And the output results is not as good as pixel CNN or pixel RNN or GANs, which we are going to cover in the next lecture. So this is it. And we are going to continue our discussion in the next lecture about GANs. Okay, let me stop recording here.